Back, section 5.4, average value of a function. Suppose f is a real valued function defined on a closed interval ab. We want to understand the meaning of the average value of the function f on the interval ab. Now you see, suppose you choose certain n real numbers in the interval a to b. Say choose x1 star, x2 star, xn stars. Choose some numbers there. Then you know the meaning of average of the values of f on these numbers. So that's an approximate average of f, that is f at x1 star plus f at x2 star all the way until f at xn star. So add all these guys up, divide by n because those are the total number of numbers you choose. But you see, an interval has infinitely many numbers. So you cannot possibly keep adding the values of f for each number. All right. So we need some way of understanding this average value. You take your interval, closed interval AB, divide it into n sub-intervals of equal length. Then the length of each subinterval is b minus a over n. Because there are n subintervals, total length of the whole interval is b minus a. You divide that by n. That's the length of each subinterval. That is delta x. Delta x represents length of each subinterval. That's b minus a over n. Now choose these numbers x1 through xn so that each xi star is from the ith subinterval. Okay, so make sure each one, so x1 star is in the first subinterval, x2 star is in the second subinterval, and so on. Now what is the same approximate average? Well, in the numerator I'm adding the values f at x1 star, fx2 star, and so on. The sum of the values of f on these chosen xi stars divided by n. Divided by n. Well, the width of each rectangle is b minus a over n. So cross multiply, you notice n itself is b minus a over delta x. So look at that. That's something in the numerator. Denominator itself is a fraction. So division by a fraction is multiplication by the reciprocal. In other words, delta x comes up, b minus a stays down. So now noticing this, we are actually able to define the actual average of f over the closed interval AB. Let's denote it by f for average, that is limit of n approaching infinity, all of this. In other words, you're making your intervals, number of intervals, go to infinity. In other words, each subinterval is going to get thinner and thinner and thinner, right? So n approaches infinity. So this is very much similar to the limit of Riemann sums, okay? So it's the same theory we are using, limit n approaching infinity. You rewrite this as follows. The numerator is nothing but summation I going from 1 to n of fxi star. Delta x is delta x, b minus a is b minus a, and limit n approaching infinity. So you know when limit n approaches infinity of such an expression, that summation becomes integral. My interval's limits are the limits of my integral. Numerator is fx, delta x, basically you replace it by dx divided by b minus a. So b minus a is a constant. It is not dependent on x. I can bring it out. So that is the average value of a function over a closed interval AB is 1 over b minus a integral a to b fx dx. For example, so remember this. Find the average value of the function fx. This is my function 3 plus x cubed on the interval 0 to 3. I don't even need to graph this, right? Average value, by definition, 1 over 3 minus 0, right? Length of the interval, length of the interval, then the integral with the limit 0 to 3 of fx dx. That's it. The rest is straightforward calculation. You're taking integral of 3 is 3x. Integral of x cubed is x fourth over 4. 3 minus 0 is simply a 3. Limits of integration are 3 and 0. Okay. So I've maintained the 3 below. Evaluating this at 3. Evaluating this as 0 gives me 0 because that's a 0, that's a 0. So all I need is a value there. 3 times 3 is 9. This is 81 over 4. Simplify. All of that gets me 39 over 4. Okay, that's an example. So what is average? It is 1 over length of the interval, integral limits of your interval fx dx. So it's basically area under your curve divided by the length of the interval. We'll continue with the next theorem in our next video.